I want to continue talking about chemical reactions, and then we'll do the lab, start the lab. The question was about the chemical properties of HCl. Well, the first one is it's soluble. Is that a chemical or physical property? Physical. And it's a strong electrolyte. Chemical or physical?
Physical. Yeah, physical.
That's, yeah, it's still HCl, it's just broken apart into ions. And what ions does it break apart into?
H plus and Cl minus.
Yeah, H plus and Cl minus. But H plus is not so stable. Do you know why?
Because it has no electrons.
Yeah, it has no electrons, it's just a what?
It's just proton.
It's just a proton, the nucleus. And if you think about the charge density would be extremely high compared to other +1 ions. So even a lithium ion is huge compared to this. And so it's unstable. And so whenever we have H+, it's going to attack water, or water is going to attack it. You know, there are two ways of thinking about it. And when water, is present, the two ways of thinking about it is in terms of Bronsted. In Bronsted, the acid is a proton donor, the base is the proton acceptor. And so in this case, water is going to act as a base and accept this proton. In terms of Lewis, we think of it a little bit differently. In terms of Lewis, did I talk about acid-base yet or not? I did? Okay. In terms of Lewis, what is the acid, what is the base?
The acid would be H because it's.
Well, I mean the definition. In general, Lewis acid is what? How do you define a Lewis acid?
Lewis acid. An acid.
No.
No electrons.
Close. Well, actually, electron pair acceptor. In other words, when we think about Lewis, it's the electron pair that's going to attack this. This makes sense because this oxygen is, the oxidation state of this oxygen is -2. The formal charge of this oxygen is
6. Wait.
not 6. Okay, the oxidation state is -2. The formal charge on this oxygen is 0. Okay, again, the notation here is I'm going to put parentheses around oxidation states and circle the formal charge so that we don't ever cross-compare them. Well, anyway, the reality is the charge of the oxygen and water really -2? No. Is the charge on oxygen and water really 0?
No.
Yeah, that's what these are the apparent charges on the atom. The actual charge is what we call something in between. And how do we represent something in between 0 and -2? Delta. And so this is a delta minus. Here. And so these are 3 ways of representing it. Normally we just look at it, oxygen's delta minus, what's it going to be attracted to? It's going to be attracted to positive charge. And so normally when we think about Lewis acid-base reactions, we think about the base attacking the acid. It's always the base attacking the acid. And we don't really think, about the proton transfer in Bronsted. Normally we think, okay, here's the electron pair, it's going to attack the acid. And in this case, what does it form?
Hydronium and
Well, in this case, we only actually form just the hydronium. Because if it were 2 waters coming together, then yes, we're going to form hydronium and hydroxide. That would be called water autoionization or self-ionization or self-reaction. In this case, it's just the H plus and the hydronium, and so it's balanced here. Let's take a look at hydronium over here, the ion. What's the oxidation state on oxygen and hydronium?
-3.
-2. 2. Negative 2. The formal charge?
Oh, 0.
Plus 1. And so in this case, we don't do these delta minuses. This has a full formal charge. When it has a full formal charge, we write it like this. And the charge on oxygen is expected to be plus 1 in this. Although the negative 2 is for redox, we can still, it still has the octet. And the formal charges on the hydrogens are all 0. And so what we use to represent the structure depends on what we're looking at. You know, if I'm analyzing this particular reaction, I wouldn't care about the oxidation state. Actually, I wouldn't care about the formal charge on water because it's not going to tell me much. What I care about is the delta minus on water. The delta minus on water here, the oxygen on water, is going to be attracted to the H plus on the acid here. We also have delta pluses on the hydrogens over here. What happens in hydronium is this. You know, water normally has an electronegativity on oxygen of 3.5, but now the oxygen has a positive charge. That's a literal positive charge here. Now, if we have a positively charged oxygen versus an oxygen with 0 formal charge, the electronegativity is going to be quite a bit different. What's electronegativity going to be here? Is it going to be higher or lower than 3.5?
Lower.
Lower, meaning it doesn't want electron, doesn't want negative. It actually becomes higher. And so what that does is it sucks the electron cloud away from hydrogen towards oxygen and makes these hydrogens much more positive. In other words, it makes these hydrogens much more acidic than these hydrogens in water. And so when we're thinking about acid-base chemistry, we typically look at delta pluses and formal charges. Delta pluses, delta minuses, and formal charge. Now, could this lone pair attack another H plus? What do you think? Will this lone pair, because we know that Lewis bases are electron pair donors, so there's one more electron pair on oxygen. Will it attack?
No.
Yeah, you wouldn't expect this oxygen to attack another H plus. Why?
Because they have a similar charge.
Yeah, they're the same charge, and you know, chemistry is electrical.
They repel.
They're going to repel each other. And so this oxygen now is no longer basic. Basic meaning electron pair donor. This oxygen is basic. There are better ones. For example, this one. What's the formal charge on this oxygen here? Not negative 2. Close. -1. Which of these 3 oxygens is the most basic? This one here, right? This is going to be the best base. So hydroxide is going to be much better base than water. Water is going to be much better base than hydronium. You wouldn't expect hydronium to be a base at all, really, because it really doesn't want to donate that lone pair. Let's do one more example here. Oxide. What's the formal charge on oxide? -2. Okay, out of these 4 oxygens, which one's going to be the strongest base?
Oxide.
Oxide. This is going to be the most basic. Here. So oxide is better than hydroxide for sure. But once we form hydronium, okay, then this is very unstable. So this is a downhill process. You know, downhill, we're going to something more favorable from something less favorable. That's what I call the driving force. The driving force is we're looking, you know, in general, we're looking for forming more stable products than reactants. And so what we want is like a downhill energetically in terms of energy. We want a downhill reaction. And so this would be still hydronium's pretty reactive. Is this a chemical or physical process here? Yeah, this is a chemical process. And this could be termed a Bronsted acid base. It could also be termed a Lewis acid base reaction. Bronsted acid would be the HCl. It's donating the H plus for this reaction. So it's a strong electrolyte, and then we looked at the metathesis. H plus reacts with all base anions stronger than water, and then chloride likes what cations? Silver, lead, and mercury. One, yeah. All right, then we move on to acid base. So let's take a look at acid base next. In acid base, I'm going to treat H plus and hydronium equivalently. H plus because we get tired of writing H3O plus all the time. It's just a lot more writing. And so oftentimes I won't bother writing H3O plus because it's just easier to write H plus. And in fact, that's going to be the case here. There are some instructors that prefer H3O plus for everything because it's more accurate. But even H3O plus isn't 100% accurate. There are higher, where water clusters together to form little clusters and of multiples of this. We aren't going to talk really much about those, but you can find those. Wikipedia. And so this is acid. Okay, over in metathesis, we said that H plus, the cation, likes any anions that's a stronger base than water. But over here, when this is acid, then it doesn't matter if it's an anion base or any base. Okay, this acid reacts with any base stronger than water. And so an example would be ammonia. Ammonia is stronger than water. And so again, I could write H plus or H3O plus. I'm just going to write H plus. H plus will react with ammonia. What forms? Okay, we can treat this as a Bronsted, or we could treat this as a Lewis in analyzing this. It's just going to form ammonium, yeah, an H4 plus. Can ammonium act as a base?
Yeah.
Ammonia can act as a base. Ammonia, when I analyze ammonia, what's the delta on nitrogen? Is it delta plus or delta minus? Nitrogen. It's delta minus. And so we could see that this nitrogen being delta minus, and it has a lone pair, will attack the H plus to form this. Okay, once we form this, is ammonium, could it possibly act as a base? No. Number one, there are two ways of thinking about a base. One, could it be a proton acceptor? It can't be a proton acceptor because there's nothing to attract or to bond the proton with. In other words, could you draw, if this were a proton acceptor, so for example, if we had NH4 plus an H plus, what would we form? We would form NH5 plus. Do you expect NH5 plus to exist? No. One of the reasons is we can't draw a Lewis structure for this. One, we'd exceed an octet. Is it possible to exceed an octet on nitrogen?
No.
No. And two, there are no electrons to bond that. Hydrogens are terminal. Although there are some examples of bridging hydrogens, but I'm not going to talk about those. So we can't draw the Lewis. So this doesn't happen. Ammonium. Two, in terms of Lewis, there's no lone pair. Not only is there no lone pair, what's the charge on nitrogen in ammonium? It's +1. This is the actual charge on the nitrogen, and so that goes to plus here. And so in this case, the formal charge is the charge on that. Okay, so we just consult the chart, and then we can see what bases are stronger than water. So let's do another one here. If I take H plus and, do you know a base that's weaker than water? Can you think of a base that's weaker than water?
Hydronium.
Hydronium is going to be on the acid side.
HCl?
Well, HCl is the acid, and this is going to be on the acid side.
Okay.
Think about the base side. Probably I need to give you the chart, huh?
Oh, wait, no, I can pull one.
Well, let me give you one. How about bromide? Bromide is a base that's weaker than water. What do we expect?
We expect it not
That's a base that's weaker than water. We expect NR.
no reaction.
No reaction. That's what we expect. You know, what we predict to form is HBr. You know, but that's just going to be NR because HBr we already know is a strong electrolyte. There are many ways to interpret this, but one is HBr is already a strong electrolyte. The H plus and the Br minus are separate. Let me okay, why we have, yeah, can I explain more why we have no reaction? The driving force is to go from stronger to weaker. So we want to go in this downhill direction. And so what we're looking for is to go downhill in terms of acid, also in terms of base. But this chart is flipped over. HClO4 is the strongest acid on this chart. And then from HClO4 it just goes downhill from there, correct? So what we want to do is we want to go downhill in terms of the acid. We also want to go downhill in terms of base, but ClO4 minus is not the strongest base. What's at the top of the hill in terms of base strength? And so the strongest acid on this chart is HClO4. What is the strongest base? Well, let's scroll down and see what the strongest base on this chart is. And so what is the strongest base on this chart? CH3 minus. If somebody just said CH3, they think, oh, you're talking about methyl, not this. This is not methyl. This is methide. And so methyl and methide are quite a bit different in terms of species. This is going to be even more reactive than methyl. But anyway, but methyls are substituents. They'll attack things and attach to them. But anyway, we're here. This is methide is the strongest base, and then this is at the top of the hill. So downhill would be up in this way. Does that make sense? So it's inverted because of the what we called it the conjugate relationship. Remember the seesaw relationship. If the base is very strong, its conjugate acid is extremely weak. And so methane isn't even considered an acid. Nobody considers methane an acid. I mean, if you're trying to do a titration, neutralizing a base with methane, you're not going to have any success. You know, so if we had, even with sodium hydroxide, let's say we had a strong solution of sodium hydroxide, it's not going to work. And so there are different ways of thinking about this, but probably the easiest is just to memorize a pattern. You know, because we like patterns in science. So probably the easiest is to memorize the. This is the pattern you might have seen in Chem 4. You know, it's a zigzag pattern. And so this is why I wrote it as HBr, so we could think of it in terms of the zigzag pattern. We take hydronium or H plus and react it with which base? Bromide. And so hydronium plus bromide yields
No reaction.
HBr. Are we going downhill?
We're going up.
We're going uphill. Is that favorable or unfavorable?
Unfavorable.
That's unfavorable. We need to go downhill. And so what we're doing is we're replacing HBr, much stronger acid than hydronium. Now, funny thing happens in water. The funny thing that happens in water is this. None of these acids can exist in water. All these acids are too powerful to exist in water. Because you know what they're going to do? They're going to attack water right away, or water is going to attack them right away. And so the strongest acid that can exist stably in water is hydronium. And so this is why there's this border here. And so all these acids above here are too powerful. You aren't going to find them in water. Instead, these will attack water, and you know what they form when they attack water? So I need to talk about this here. Do you know what this is called?
What is it called?
Well, do you, what is it called?
For what? What was the question?
Um,
The answer.
That all those acids are so strong. The organization of there's something that's related to. How about this? We'll just use Wikipedia. Wikipedia. All right. In chemistry, hydronium is the common name for the aqueous cation H3O+, the type of oxonium ion produced by protonation of water. I don't know if that's so useful there. This is a take-home point. Any acid that is stronger than H3O+ reacts with water to form hydronium. Therefore, no acid stronger than H3O+ exists in water. For example, aqueous perchloric acid, aqueous hydrochloric acid, and aqueous nitric acid are all completely ionized and are all equally strong acid. So I told you HClO4 was the strongest. In fact, in terms of ranking, it's HClO4, and then HCl is weaker, and then HNO3 is weaker yet. But all these are plenty strong enough to react completely with water. And they all result in the same amount of H3O+. The amount of H3O+ is going to tell us how good an acid it is. Strong acids yield lots of hydronium. Weak acids yield less hydronium. So this is called the leveling effect of strong acids. In other words, they all yield same amount of hydronium. Therefore, they all have the same strength in water. So basically, there's going to be a tug-of-war. The tug-of-war is going to be between H2O and ClO4 minus. H2O versus ClO4 minus, who's going to win the proton?
HCl. Right. Water.
H2O. Okay, there's going to be a tug-of-war now. H2O versus HCl, who's going to win the tug-of-war?
Water.
And H2O versus HNO3,
Water.
water is going to win.
Is the base.
In fact, water is going to have no problem plucking the proton off all three of these. And therefore, none of them were strong enough to provide any resistance to water for that. However, if we look at something like acetic acid versus H2O, here acetate is going to provide a significant fight against water. Acetate's a base, water's a base. We have these two bases competing for the H+. Who's going to win?
Acetate.
Well,
Well, most acid could be a good fight, but most likely be water.
well, yeah, it turns out that acetate is actually quite a bit stronger than water, but water can pluck off some of them, and so we form a little bit of hydronium plus acetate. To show this, we show it in different ways. One way we showed is uneven arrows. So the downhill direction is here towards the reactants. And so we can see this here. So if we have acetic acid versus water to form hydronium, is that favorable?
No.
No. That's not favorable. Versus if we have HNO3 and water, when HNO3 and water react, it forms hydronium. Is that favorable?
Yes.
Yes. This is favorable. And so, in other words, the leveling effect here is important because that tells us this. It tells us that all these acids in water are the same strength. And so all these are equal. But if we have a different solvent, they aren't necessarily equal. It is a fact that HClO4 is easier to pluck the proton off. But for water, HNO3 is almost just as easy. But acetic acid is a lot harder to pluck the proton off. Do you know what the strongest base that can exist in water is? Hydroxide.
Almost got it.
And so none of these bases here can exist in water. If you tried to make a 6 molar oxide solution, forget it, you can't. Because all these bases will attack water. So for example, if I take, let's say I take methide and react it with water, it's going to form hydroxide. Well, that's going to be downhill or uphill?
Uphill.
Well, on the bases.
Well,
So if I go from methide to hydroxide, am I going from stronger base to weaker base, or weaker base to stronger base?
Stronger base, so we can make
Yeah, stronger base to weaker base. And so methide will never exist in water. And so we'll say leveling effect of strong acids and strong bases. And so if I have methide, you're never going to get this in solution because methide is going to attack water, and what is it going to form?
hydroxide.
Hydroxide and here. So methide plus water, so we go up like this, forms hydroxide and,
Methyl. I'm trying to think of the name. Methyl.
this is not called methyl,
Methane.
methane. So this is going to form methane plus hydroxide. So this is going to happen, this is downhill, this is going to happen immediately. So let's compare that to another one. Let's compare that to sulfide. Sulfide plus water. Let's do that. Sulfide plus water yields and so this is going to yield HS minus hydrogen sulfide ion plus hydroxide. That's the same. These react completely. And we call this hydrolysis of water. So strong acids hydrolyze water completely to form hydronium. Strong bases hydrolyze water completely to form hydroxide. Hydrolysis just means breaking apart of the water or reacting with the water. Here. The only tricky one is oxide. When oxide reacts with water, we form hydroxide and hydroxide. And so here we double the amount of hydroxide. So oxide is actually going to yield more hydroxide than the others. This is just the ability to pluck a proton off. How strong of a proton plucker is it? The methide would be the strongest. But it doesn't matter in water. The water are easy protons to pluck for all these. There's no problem. When we get to weaker acids, then it becomes more difficult to pluck the proton. So what was I talking about earlier?
Chemical properties.
Okay, chemical properties, HCl.
We were doing acid base.
Okay, so in other words, hydronium. So in using this pattern, will hydronium react with nitrate? What do you expect? No, we don't expect hydronium to react with nitrate because what would the products be? If hydronium reacted with nitrate, it would form HNO3. And is HNO3 a weaker acid or a stronger acid? Stronger acid, so we don't expect this. We expect no reaction. Will hydronium react with trichloroacetate? Yes, because if hydronium reacts with trichloroacetate, it's going to form water and trichloroacetic acid. And so this would be favorable. In fact, hydronium will it react with sulfate? Yeah, it's going to form bisulfate, weaker acid. Will it react with dihydrogen phosphate?
Absolutely.
Yeah, phosphoric acid forms. Will it react with, you don't need to know this. This is Chem 1B. This is iron 3. Will it react with nitrite?
Yes.
Yes. Okay, now let me test you on the leveling effect. If you understand the leveling effect or not. I'm going to take my HCl and react it with, what's this called? ClO3 minus. Chlorate. So HCl and chlorate, will that react? Well, okay, HCl and chlorate should form HClO3, which is called chloric acid. So we're going from hydrochloric acid to chloric acid. That's downhill, isn't that?
Yeah.
So do we see a reaction? Yes reaction, no reaction.
Yes.
There is a reaction.
Yes reaction or no reaction or
Or
yes no
yes.
reaction or whatever.
Yes, there is a reaction.
There is a reaction. You're certain about that? There's going to be a reaction there.
You're making me second guess myself.
Yeah,
Equal strength.
they're equal strength. This is actually a tie. It doesn't look like a tie, but it's a tie because it's in water. And this is called the leveling effect. All these are equal in the pool of water. In the pool of water, you can't tell the difference because they all produce the same amount of hydronium. However, if this wasn't in water, then you would be right. If this was not in water, we would expect reaction. So if this were gas phase, then yes, there should be a reaction. And so this is the complication of the leveling effect. It's a tie. Okay. And therefore, no reactions expected. So if I said HCl, what bases does it react with? You'd say, oh, all bases stronger than chloride, but it wouldn't react with these. You know, and so it gets tricky. This is kind of why I split it up. Instead of calling it HCl, I call it hydronium because HCl is a strong electrolyte, breaks apart into those. Okay, now let's take a look at the base. So that was the acid. When we have HCl, we have H plus or hydronium, and we have Cl minus. Cl minus is a base. So what acids does Cl minus, the base, react with? So what we'd say is Cl minus, the base, should react with all acids stronger than HCl or weaker than HCl.
Weaker than HCl.
Now the base, we have to be careful because it's flipped. The strongest base is actually at the bottom of the chart here, and then we go weaker from there. And so let's just go back over here and look. So we did methide plus water. Methide plus water yields hydroxide and methane. So if we go from methide to hydroxide, are we going downhill or are we going uphill?
Going uphill.
We're going up.
Downhill.
We know that.
Going the wrong way.
Yeah, so when we go from methide to hydroxide, we're actually going downhill in terms of the bases. And so maybe I shouldn't use downhill and uphill. What should I use instead of downhill and uphill? Because you're right, we are going uphill, but uphill is actually downhill in the base universe. So we should use something different than that, right?
Strong to weak.
Yeah, maybe that's probably the better. Stronger to weaker. That's usually what I say, stronger to weaker rather than uphill and downhill, because uphill and downhill means it depends on what chart you're using, because if we're using just a base chart, then downhill would probably be downhill. And so we have to be careful. And so a much more generic way of saying this is, are we going from stronger to weaker base? Yes. Is that favorable? Yes. We want to go from stronger to weaker because stronger is more reactive, higher energy, weaker is less reactive, lower energy, so stronger to weaker. And that's favorable. How about the reverse? If I take phosphate and water to form hydroxide, are we going stronger to weaker? No, we're going from weaker to stronger. That's not favorable, right? That's not favorable. So let's go back up here, and I'm going to ask you, I got an idea. Chloride is a base. It'll react with acids that are stronger. Let's just use the strongest acid, HClO4. So we're going to go from chloride, and we're going to go to HClO4 to form perchlorate. So now look at chloride to perchlorate. That's going from stronger to weaker, isn't that?
Yes.
And therefore, isn't that favorable?
Yes.
Except this is in the leveling effect zone.
Yes.
In the leveling effect zone, we have to think differently because this is a different zone of the chart. And so, for example, if we look at the acids, we're going from HCl to HClO4. Is that favorable?
No.
No, it's not.
Oh, that's not favorable. And then chloride to perchlorate, that would be favorable, wouldn't that? But anyway, this is the leveling effect here. All these bases here are so weak that they're not considered bases. They're considered neutral. And so there are different rules that people memorize. The rule in our book says this. This is in chapter 14 or something. And that is, the conjugate bases of the strong acids are too weak to be basic in water. And so in other words, the conjugate bases of the strong acids are too weak to be basic in water. That's one way of putting it. And this way is good in terms of what makes these acids a good electrolyte. What makes these acids a good electrolyte is because the H plus easily breaks off. If the H plus easily breaks off, then that means these conjugate bases here, these anions don't have much of an attraction for H plus, otherwise they wouldn't let it go so easily. And so these are too weak. And then there's another thing, another way of thinking about it is in terms of leveling effect, because here we aren't going in terms of, you know, if we're saying, okay, we're going to take chloride and react it with HClO4, if we take chloride and react it with HClO4, then HClO4, that's going to produce ClO4 minus and HCl. So if we take chloride and react it with HClO4, then HClO4 is the reactant, is going to go down to HCl. Maybe I should write it down so you can see it. And so a lot of you, this is the way I usually write it. So we're going from a stronger base, which I call SB. It's not a strong base, it's just stronger than this. This is a weaker base. And we're going from a stronger acid, SA I call it, to a weaker acid, WA. But what do we know about this? We know that this is not the case. This is not stronger, this is not weaker. This looks favorable, doesn't it?
It might be, but forget
Not in water. These are all aqueous.
But don't forget that they're on equal states.
And we know that these two acids in water are actually not different, they're equal strength.
Or on equal states in terms of leveling effect.
Yes. And therefore these bases are actually equal as well, equally bad. And so what that means is there is going to be no reaction. I mean, if you said, okay, chloride's going to react with any acid stronger than HCl, no, it's not going to react with any acid. In fact, we call chloride neutral. It's too weak. And so we'll put a base and we'll put a little asterisk here. This is too weak. Therefore, we call it neutral. So let's say you ran out of antacid. If you ran out of antacid, would you just take some table salt and just maybe eat some table salt to help neutralize the acid in your stomach? You think it's going to work? It's not going to work at all. I mean, sodium chloride, chloride is too weak. It's not going to pluck any protons off, anything, and neutralize it. All right, so when you're in this zone and that zone, right, it becomes a little more trickier. But if you're in this area, or if you take, let's say if you're strictly in this zone. If you're strictly in this zone, then yeah, that's the case. But if you take one of these, you know, and react it with one of these down here, then it's a little easier to deal with. But let's do this down here. Let's make something a little bit easier. Let's take two of the acid anions. This one, what's this one called?
Bisulfate.
Bisulfate, and let's take this other one here. What's this one called?
Bicarbonate.
Bicarbonate. So we're going to take bisulfate and bicarbonate. Do you expect a reaction between bisulfate and bicarbonate? What would it form? So if we took bisulfate and bicarbonate, it should form sulfate. So are we going from stronger base to weaker base? Yes.
Yes.
Okay, and what's going to happen to the bisulfate? The bisulfate should form CO2 and water. Are we going from stronger acid to weaker acid? Yes, so we expect reaction. So if we took bisulfate and bicarbonate, they should react. The products would be sulfate and CO2 and water.
And water.
Or carbonic acid, as they have it in quotes here. Oh. Okay, what if we took H, not HF, let's let's take this. Let's take, HCN. I'm going to try to neutralize HCN using bicarbonate. HCN and bicarbonate. Is that good?
No, it won't.
No, because if I took HCN and bicarbonate, it's going to form CO2 and water, aka carbonic acid. And carbonic acid is stronger or weaker? Stronger, so we're going from weaker HCN to stronger. And then the same thing with bases. In terms of bases, we're going to go from bicarbonate to cyanide. Cyanide is a much stronger base than bicarbonate. So this is uphill. This is not favorable. So getting back to chloride, chloride as a base is pretty much neutral. Yes, maybe if we had a super acid, could react, but other than that, you don't expect anything. All right, then one final thing for HCl properties are redox. So do you feel okay with this? This is called the chart method. Uh-huh. I'm going to post it on Canvas. If not, I thought maybe it is. I don't remember. Does anybody?
You looked at, I think it was Plaza to get this, or Piazza?
Yeah.
Yeah, that's how you found this.
I'll post it on Canvas.
Oh, 21, section 1, strip from
This is the redox chart here. It looks a lot less clean than the acid-base. Acid-base chart's simple because we're only looking, that's called the Bronsted acid-base chart. That's not the Lewis. If we had the Bronsted and the Lewis acid-base chart, it would be pretty messy. In fact, I forgot to talk about other Lewis reactions, but it's okay. As long as you know the basics, electron pair donor, electron pair acceptor, you're okay. Lewis, let me just make a note here. The chart that we just used is the Bronsted chart. Lewis are more complicated. And so we'll take a look at Lewis later in more detail. But for the redox, this is it. There's a simpler chart called the activity series. The activity series is quite simple. And so they took all this mess here and then made the activity series. Does anybody recall in the activity series what's at the top of the activity series? Or this is for single replacement reactions. Yeah. At the top of the activity series is lithium. meaning lithium is the most active. The most active is the most reactive. And so what we want to do is whenever we use the activity series to make predictions is we want to go from more active to less active. Right? And so if we go from lithium to, let's say, zinc, then that's favorable. And so what would be an example of that? An example of that, well, these ones are so active. Let's take something like zinc and
Go from zinc to nickel.
nickel. Yeah, that's probably easier. So we use the activity series like in single replacement. And so let me just talk about redox brief. Single replacement has the form A plus BX. A plus BX yields AX plus B. And we compare A and B using the activity series. So, as an example of this, did I say zinc and nickel? Or
Yes.
Yes.
Okay. We'll take zinc metal plus nickel 2 chloride. And so this is my A, this is my BX. This is going to yield what?
Zinc chloride plus
Zinc chloride. What's the charge on zinc ion?
2.
Yeah, it's fixed. There's only one charge, it's 2. So we're going to form zinc chloride and nickel metal. And then we look, are we going downhill? So we're going from zinc to nickel. Is that downhill?
Yes.
Yes, that's downhill. And since that's downhill, then we say that there should be a reaction because we're going from more active zinc to less active nickel. So this is downhill, this is favorable. And so therefore we have driving force for this particular reaction. That's how we would use it. Do double replacements fit in redox? No. What other types of redox reactions do we have in addition to single replacement? Well, in terms of redox, probably we'll start off with, let's look at redox. The element plus element combination, and the reverse would be decomposition. And so element plus element combination would be, let's say I wanted to make nickel chloride. One, I could just take nickel metal and react it with chlorine gas. What's the oxidation state of nickel and nickel metal? Element plus element combination and the reverse, which would be decomposition.
It should be +1. Nickel.
Nickel metal, the element, has an oxidation state of 0. Chlorine, the element, Cl2, has the oxidation state of,
-1.
well, you can't have, minus 1 times 2 would be minus 2, and that's not the charge on chlorine gas. Chlorine gas is 0. What does this form? It forms nickel 2 chloride. What's the charge on nickel 2? And the charge on chloride? Oxidation state? -1. And so this is a redox reaction. The forward direction is called a combination. The reverse direction is called decomposition. So we can decompose nickel 2 chloride into the elements nickel and chlorine by a chemical process. That chemical process is redox. And so this element plus element combination. And then we have single replacement. And then we have combustion. And then we have the chart method. And then we have the skeleton redox. Single replacement, advantage is it's fast. Disadvantage to using this method is it can be wrong. Disadvantage is it fails for certain types of species. So if you use single replacement, it's a nice simple pattern. It's quick to predict, but sometimes you could be wrong, and so you should know the exceptions to single replacement. The chart method, the advantage is you don't have to memorize the exceptions. It should work. The disadvantage is it takes more time. And so I don't really spend much time with single replacement. Instead, I just use the chart. That way we don't have to worry about this. And so advantage over single replacement is you don't have to memorize the exceptions. Do not have to memorize exceptions. The disadvantage is it's more work. Than single replacement. So let's talk about redox in general, and then we'll come back to HCl. Oops, I forgot to point it over this way. Now if you can see it. So let's just look at some example redox reactions. When you look at this reaction, what do you think? Shouldn't be too hard. Sodium plus potassium chloride, that's A plus BX. What does this yield?
Sodium chloride plus potassium.
Sodium chloride plus potassium. And then we look at this. Sodium versus potassium. So no reaction.
There's no reaction.
We expect no reaction. But what I should say is no reaction for this. Don't do this. Don't put sodium in aqueous potassium chloride because you'll have a violent reaction. You'll have a violent reaction because sometimes, and this is something that we're going to start doing, is this. We're going to do this for the chart method. You know, the chart method is more work, but we don't have to memorize these particular exceptions here. Some of these exceptions aren't so difficult to memorize. You know what happens when sodium comes into contact with water?
It violently reacts.
Yeah, it violently. Have you guys seen, everybody seen sodium react with water?
It can explode.
It's pretty explosive. You haven't seen it?
It's great way to clean your plumbing. It just cleans the pipes, removes your entire toilet, breaks it in one shot.
The have soda a lot, right?
I remember lithium doing something similar. Like if you take a lithium battery and unroll it and put it into a pan of water, it has a chance of exploding just outright.
Put any of that sodium in water.
Probably seen them.
Highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government's liquid chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Do that just to kind of have fun.
People do it all the time to have fun.
Yeah. Nice pyrotechnic show.
Actually, one of the labs at UCSB burnt down. Have you heard this?
No.
One of the one of the graduate students there had just a tiny bit of sodium, and so, what do you do with it? Well, he was thinking, he'll just get rid of it by tossing it into the sink and then letting it react with water. It's not going to create a massive explosion like this, but it'll catch on fire, make a little fireball. But it's in the sink. Sink's full of water. He thought it was full of water, but the other lab mate, there are two people in the lab, poured some organic liquid down the sink and it caught on fire. And it was actually quite a lot of organic liquid. Maybe it was acetone or something. And it ended up burning down the lab there. But yeah, people do that all the time. All right, but the problem with this is you have to think of other things. And so if you get locked into a pattern, A plus BX, then you're kind of locked in that pattern. And if it's not that pattern, then you can't kind of figure things out. And so probably a more difficult but better way of doing things would be to use the chart method. And with the chart method here, we aren't locked into any pattern. And so what we have is we have solid sodium plus KCl aqueous. And in the chart method, the first thing is we inventory everything present. And so everything present is we have sodium metal, and then potassium chloride. It's soluble, it's aqueous, all group 1 salts are. Is it a strong electrolyte? KCl aqueous. Soluble salts are strong electrolytes. So what do we expect in a solution of KCl?
K plus Cl minus.
K plus and Cl minus. Okay, here we aren't locked in the pattern. We got to figure out what else is present.
H2O.
H2O. And can H2O react?
Yeah.
Yes, H2O can react in acid-base reactions. Right? H2O is both an acid and base. And it can react in redox reactions because H2O is both what we call an oxidizer and a reducer. And so it can react. So we aren't locked into an A plus BX pattern. We're looking at things completely. Now what we do is once we inventory, we aren't going to use the activity series. The activity series is too limiting for us. So what we're going to do is we're going to use the redox chart. And we aren't going to use the activity series, but the activity series is on the redox chart. Do you see the activity series on the redox chart?
Yes.
Yeah, it's just upside down. We have an upside down activity series here.
Lithium, correct.
Lithium, potassium, this is the activity series. And so if we're using the activity series, we got to invert our way of thinking. Rather than going down like we did over there in the activity series, we got to go up because up is the downhill in terms of the activity series. Okay, we have names for the sides. Like, for example, in the acid chart, on the left were the acids, on the right were the conjugate bases. They're conjugate pairs. The same thing in redox. If lithium is very reactive, how does lithium react? Lithium loses an electron because, did I write that up here? No, I didn't. But the same thing with sodium and potassium here. When sodium reacts, what happens? Sodium loses an electron to form sodium ion. So that's what we had here. If we look at the oxidation state of sodium metal is 0. The oxidation state of sodium in sodium chloride is +1. So to go from 0 to +1, we must have lost an electron. So that's what happened there. And over here, potassium ion is +1. And potassium metal is 0. And then over here, chloride is -1. And over here, chloride is
Still -1.
yeah, it's still -1, so nothing happened to the chloride. And so in other words, sodium and potassium here. So sodium is less active, potassium is more active. So what that means is potassium loses electron easier than sodium, being more active. And which one loses the electron easiest?
Lithium.
Lithium is at the top, therefore it loses the electron easiest. If lithium loses the electron easily, then its conjugate species, which would be lithium ion, does that gain an electron easily? No. Lithium ion has a hard time taking electrons because it doesn't really want them. Lithium, well, technically it's not absolutely correct because it is positive, but in other words, it's very easy for lithium to lose an electron because Li plus doesn't hold on to that electron tightly. If Li plus held on to the electron tightly, then we'd be left with lithium metal. At the opposite end of this, so lithium loses an electron easily, but what about fluoride?
Fluoride has a really hard time.
Yeah, fluoride has a really hard time giving up an electron. So fluoride doesn't want to lose any electrons. And so, in other words, fluoride is the least active. Lithium is the most active. So fluoride's the least active. It doesn't want to lose any electrons. And its conjugate must really like electrons. What is its conjugate? Fluorine. And so fluorine must really like electrons because once it gains those electrons, it holds on to them. It doesn't let them go. And so fluorine has a different type of activity. Fluorine's activity, what takes electrons? Oxidizers or reducers take electrons? Oxidizers. Fluorine is the most powerful oxidizer on the chart. Reducers lose electrons, so fluoride is the weakest reducer. Fluorine's the strongest oxidizer on the chart. What's the weakest oxidizer? Well, the weakest oxidizer is going to be lithium plus. This is the weakest oxidizer because this doesn't really want electrons. So there's a conjugate relationship here, just like in the acid-base chart. So on the left, we have the oxidizers. They take electrons. So all these are gaining electrons. And on the right, we have the reducers. All the reducers lose electrons going backwards here. And we don't want to make two different charts. We make one chart, just like with the acid base, we make one chart. But let me take that back. This has two charts, unfortunately. This has one chart labeled acidic and neutral. It's labeled acidic here, but it's for acidic and neutral. And then there's another chart here for basic. The problem is the water. Do you see where's water? Water is at the bottom of the chart. And so, what does that mean? I said lithium ion is the weakest oxidizer, but isn't water the weakest oxidizer because it's at the very bottom of the chart? No, it's not. And so what we have to do is we have to use this number here. These numbers we use in Chem 1B. In Chem 1A, we just use this number for positioning. And so if we look at it, it's minus 0.8, which positions it between what two?
Aluminum and magnesium.
Well, actually
Sorry.
aluminum and zinc. And so water actually belongs here. Do you see what I drew 3 dots right there? That's where you insert water. And so that means water is more powerful than aluminum ion, but less powerful than zinc ion. And the same thing for the reducer, hydrogen. Hydrogen is less powerful than aluminum, but more powerful than zinc, because we're reading this upside down. And so that's where we insert water here. Okay, so what we're going to do is we're going to inventory these and then identify these as oxidizers, reducers, or both. So if I have sodium ion, is sodium ion on the left side or the right side of the chart?
Left side. No, right side.
Right side or left side?
Left side.
The left side.
Left side. Yeah, I see sodium on the left side here.
Sodium ion.
No, I don't see is that sodium ion?
Yeah, so like,
No, it's actually not sodium ion. I made a mistake here. Do you see? This is sodium
Acid.
metal. I wrote sodium ion. Are they? No. Do I have any sodium ion here? What's the oxidation say? It's 0. That's not sodium ion. Sorry. This is sodium metal. There's no charge on sodium metal. It's 0. And sodium metal is on the left side or the right side?
right side.
It's on the right side of the chart. And the right side we call oxidizer or reducer? Reducer. So I'm going to call this RA. You know what RA stands for? Reducing agent. Okay, potassium ion, left side or right side?
Left
Left side.
Left side, so that's an OA. Chloride. So let's take a look. Left side or right side?
Right side.
The right side.
So that's a RA. And then water. Water occurs on both sides. Here's a water here. Look at this water. Wait a minute, here's another water. You see? What's the difference? I got 2 waters here. Which one should I pick? Does it matter?
Yes.
Which water should I pick?
The one that was formed from Chem.
Should I pick the weaker water or should I pick the stronger water?
The weaker water.
I should pick the weaker water. Why?
Because it gets us closer to an answer if we have weaker water. Less influential in the
Well, in terms of reactivity, which one do you think is going to react first? The weaker water or the stronger water? In terms of reactivity, if H2O is going to react, is it the stronger water that's going to react or is it the weaker water that's going to react?
the stronger water that's going to react.
Yeah, the stronger water will react, right?
A weaker, okay.
But does that make any sense at all? Why would, if I have 2 H2Os, what's going to define it as being stronger or weaker?
How it was made.
They're the same. Okay, let me tell you what's going to define it as weaker or stronger. It's not the one. It's the product. This H2O, if it reacts, what does it form?
O2.
If this H2O reacts, what does it form?
H2O2.
H2O2.
Which one's more stable, O2 or H2O2?
O2.
O2. And so this one is going to be more favorable because it's going to form some more stable products. And so we're going to pick the stronger water because it's going to form more stable products than the weaker water up here. And so we pick this one. So water occurs on the right side. On the right side we call it a,
RA.
but water also occurs on the left side. Where do we position water on the left side?
Between
between, yeah, zinc ion and aluminum ion right here. And so this water belongs there. And that means water is also a
Oh wait.
OA. Now water, going back to acids and bases, water can act as an acid and a base. It occurs on both sides. There are lots of species that do this, like bicarbonate. Bicarbonate occurs on both sides. It's both an acid and a base. We call those species amphoteric. We don't have an equivalent word for this, amphoteric or amphiphilic. And this is just, it can occur as both. None of these can occur as both. These only occur on one side of the chart. Okay, so we identify, and then if you're going to have a reaction, the reaction is going to be between the two weakest species or the two strongest species? The two strongest species. If you're going to have any reaction, we might not have any reaction, but what you're going to do is you're going to pick the two strongest. Which are the two strongest species? So we have 3 RAs. Which of these are the strongest? So if we go to RAs, lithium is the strongest RA. And so we'll just go up the list. Going up the list, I hit sodium first. And then chloride's way up there, and water is way up there. And so the strongest reducer I have is sodium. And then I have 2 oxidizers, potassium ion and water. So which one's stronger, potassium ions or water? Potassium ions or water? Well, water is up here. And so I should rank it. Water versus potassium ions. Which one is stronger? Well, what's the strongest? The strongest species on the left side is fluorine.
Fluorine.
And so which one do I hit first? Going from fluorine, I'm going to go down, 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 down until I hit water here, or potassium ions here. Which is stronger?
Water.
Water or potassium ions? Water. Water is the strongest oxidizer. So first I identify, next I pick the 2 strongest species. The 2 strongest species are going to give me the biggest driving force for reaction. But I don't know if a reaction is going to occur. So the next thing I'm going to do is write the likely reaction. So what does sodium do? So I have sodium, but it's not a product. I need sodium as a reactant. So what I'm going to do is I'm going to flip this reaction and reverse it. And so I'm going to just copy it off the chart. Sodium solid goes to sodium plus an electron. And then for water, I'm just going to copy the equation as is because I have water as a reactant. And so if I have water as a reactant, then I'm just going to use this. I'm going to write 2H2O liquid. I'm going to stop writing aqueous because it just takes too much time. So I'll write 2H2O liquid plus 2 electrons yields what? H2 gas plus
OH minus.
Yeah, 2 OH minus. Okay, these are the 2. These are called half reactions. So sodium loses electrons, water gains. Redox reactions we call electron transfer. But if we're dealing with a redox or electron transfer, the number of electrons transferred is not going to be correct. You see, because sodium only loses 1, but water needs 2. So it's missing 1. How can we correct that discrepancy in electron transfer?
We can have 2 sodium.
Yes. Yeah. What we're going to do is we're just going to multiply the top one by 2. So we'll have 2 sodiums goes to 2 sodium ions plus 2 electrons. And now the electrons cancel. We have to make sure the electrons cancel because redox is electron transfer. And the electrons lost by one species must equal the number of electrons gained by the other. And so the reaction is going to be 2 sodium solids plus 2 H2O liquids yields 2 sodium ions plus hydrogen gas plus 2 hydroxides. this reaction produces a lot of energy. Now, if there's air around, that energy is going to heat up the hydrogen gas and the oxygen in air and cause a explosion. And so the explosion was due to hydrogen gas exploding in the video. Okay, there is a driving force for this. Now the driving force is we want to go from stronger to weaker. Stronger to weaker is always downhill, regardless if we're going up or down on the chart. And so sodium we have as an Ra. Water is our OA. Now to go backwards, we look at the half reactions as easiest. Going backwards here, if I went backwards, then it's taking electrons. If it's taking electrons, this is the OA. So when we have an Ra, its conjugate is going to be an OA. When we have an OA, its conjugate will be a Ra. So the Ra in this case is going to be both these species here. And so the conjugate OA is sodium ions. The conjugate Ra will be hydrogen and hydroxide. This will be the Ra. Next we see, are we going uphill or downhill? So we look at sodium versus hydrogen. So if we go to sodium versus hydrogen, are we going from stronger to weaker?
Yes.
Yes, hydrogen fits right in here. So that's correct. We're going from stronger to weaker. Because of the conjugate relationship, we only have to do one of these. So we either do the acids or the base, or we can do both. But in general, we just do the acids and acid-base. Here, we only have to do one of them. So this is why we did the activity series. The activity series is, you want to go from stronger Ra to weaker Ra. That's the activity series. Because of the conjugate relationship, the OA must follow because the OAs are just on the opposite side. And so in other words, if we're going from stronger, more active, to weaker, less active, then this has got to be the case. But let's just confirm that. And so that means water must be a stronger oxidizer than sodium ion. So is water a stronger oxidizer than sodium ion? Yes.
Yes.
And so this is going from stronger to weaker. Therefore, we have a driving force here. This is downhill. And we expect the reaction to occur. So one of the reasons I don't like the pattern is because patterns kind of lock you into thinking that it's going to, it locks you into a narrow path, basically, and sometimes you miss stuff. And so we can miss something like this. There's another reason I don't like patterns, and I'll talk about that after. We'll take a break right now. I'll talk about that after the break. Let's see, what time?
It's 11:14.
Yeah. We'll take a break. So let's look at the redox properties for HCl.
You can talk to people every day.
So if we go to H+, how do you want to handle it?
A lot of people.
Do you want to just go single replacement, element plus element, combustion? How do you want to deal with H+ and then Cl-? What are the redox properties of HCl?
It is a oxidizer
It is a oxidizer. Why?
because it has a positive charge, so it is willing to accept electrons.
Yeah, H+?
Yes.
Okay, that's pretty good. What we do with this is, okay, we look, H+ is an oxidizer, you're right. It's on the left side of the chart.
And it's very far up.
So let's see, so is it a strong oxidizer? Weak oxidizer?
It is a strong.
It is very strong.
Okay, well H+ is here. The weakest oxidizer is
Down there. Oh, so it's
lithium plus, and the strongest oxidizer is
fluoride.
fluorine at the top. So what we say is it's not weak, it's actually a moderate oxidizer.
Or somewhere in the middle.
Because this is not linear. I mean, these are very, very weak
Wait,
here.
I shouldn't say me.
Yeah.
And so we consider H+ as a moderate oxidizer. It's not a powerful. Up here are the powerful oxidizers. Once in a while, it's gonna. We don't have to memorize this chart. Somebody asked me, should I memorize this chart? No, it's too much to memorize. But then again, you shouldn't ignore this chart. So what you should do is once in a while, you should read through it. You know, so once in a while you read, what are the strong, powerful oxidizers? Fluorine for sure. What's this?
Oxygen.
It's not oxygen.
It's ozone.
Ozone. Ozone's a pretty powerful oxidizer. The next one you don't have to worry about. The next one is actually a peroxide. If you looked at this, it would be weird because what would oxygen's oxidation state be? -2, and that means sulfur is,
+8.
well, this is -2 times 8 is -16.
16. Oh.
16,
It would be +7.
it'd be +7.
Yeah.
+7 times 2 is +14. +14 minus 16 gives us -2. So +7. What's unusual about sulfur being in +7? So let's take a look at sulfur on the periodic table. It's 16. Okay, go ahead.
I was gonna say the answer, but then you're gonna.
No, go ahead. Go ahead with the answer.
So I think that sulfur might be one of the exceptions in terms of oxidation states.
Okay, what is the normal range of oxidation states for sulfur?
5 minus
+6 minus 2? Yeah. +6 because if we go from 16 to 10, it'd be isoelectronic with neon. -2 because if we go from 16 to 18, it would be isoelectronic with argon. So we use the noble gas. But this is not +6. This is +7, which means it would be isoelectronic with fluorine. Is that favorable?
No.
No. We know fluorine's unhappy as is. And so it's not, and it turns out it's not, all the oxygens are not -2. There's a -1 oxygen, 2 of them, which would form a peroxide bond. Remember dichromate? The formula for dichromate's kind of weird because if you take a look at 2 chromates, we got 4 oxygens. And so you think dichromate, you just attach 2 of these together. And so dichromate should be Cr2O8. It's not Cr2O8. Why?
It's CR2.
Because this is not great here. We don't want to form what's called a peroxide bond. Peroxides are very unstable, so what we end up doing is getting rid of 1 oxygen so we don't have to form a peroxide bond, and it doesn't come out to Cr2O8, it comes out to Cr2O7. And that's because we lose 1 of those. Well, if we take 2 sulfates and put them together, you know, if I took 2 sulfates and put them together, it should be S2O7, not S2O8. This is S2O8. This is not stable. This is because it's got a peroxide link there. Peroxide link is going to make it very reactive. And so it turns out it's not +7, it's +6. So this is one of those where the average oxidation state screws you up. So this is why I like doing them based on Lewis structures. But anyway, below this is what, H2O2?
Yes.
Hydrogen peroxide followed by MnO4 minus, which is called
Permanganate.
followed by this.
Lead oxide.
It's not just lead. Lead is variable charge. What are the common charges for lead? Is that lead 2 oxide or lead 4 oxide? Lead 4 oxide. Lead 4 is kind of a high charge. You know, how many +4 cations can you think of off the top of your head?
Well, there's lead.
Then there's tin, but anyway, this is what we call electron poor. In lead 4 oxide, this is the oxidizer in automobile batteries, so this is why this is up here. Cl2, chlorine's a little weaker, and then we have dichromate, manganese 4 oxide, etc. So once in a while we'll go through and read through these. Iodate, it's interesting. It's not comprehensive, but useful. All right, so we look at H+. Which is here. So what will H+ react with? So what will H+ react with? We look at hydrogen. If H+ and hydrogen got in a tug of war, who would win for the electron?
H+.
It'd be a tie because If H plus 1, then we end up with hydrogen and H plus. And so it's kind of a tie. So we need something stronger than H2 or weaker than H2?
Stronger than H2.
Okay, so if we take H plus and what's stronger than H2? Is lead stronger or H2S stronger?
H2S.
H2S.
Like,
No, it's actually lead.
It's lead is stronger. And so what that means is H plus can strip electrons from lead, but it will not be able to strip electrons from H2S. And so when H plus strips electrons from lead, what forms? So H plus takes electrons from lead, we're going to form
Lead to
lead 2 plus. Is lead 2 plus stronger or weaker than H plus? Weaker. So we're going from stronger
To weaker.
to weaker, and this is on the oxidizer or the reducer side?
No,
Oxide. So we're going from stronger to weaker oxidizer, and then if H plus reacts with lead, we're going to form lead 2 plus and H2. Is H2O stronger or weaker than lead?
Weaker.
Weaker. So we're going from stronger to weaker. So this is the zigzag method of the chart. And so what that means is H plus, being an oxidizer, will oxidize anything stronger of a reducer than H2. So that means H plus will oxidize lead, it'll oxidize tin, iron, zinc, aluminum, etc., all the way down to lithium. However, H plus will not oxidize, will it oxidize copper? No, it won't oxidize copper because that would be uphill, H plus going to copper 2 plus. Will it oxidize silver,
No.
which is up there? Will it oxidize iodide?
No.
No, it won't oxidize any of these. So in terms of H plus will oxidize all reducing agents stronger than
H plus.
H2. Because H plus is an OA. What is Cl minus?
Cl minus is a
Yes, Cl minus is a reducer. So let's take a look at Cl minus, which is here. It's an Ra. And so we look, well, if chlorine and chloride got in a tug of war for electron, who would win?
They're both equal.
They're both equal, it'd be a tie. So we need something stronger than chlorine. So what is stronger than chlorine? Lead 4 oxide or dichromate? Lead 4 oxide. So in other words, we can say it this way. Lead 4 oxide will oxidize chloride to form chlorine and lead 2.
Lead 2.
Is there driving force? Yeah. We're going from stronger oxidizer to weaker. On the other hand, will MnO, well, let's go with O2. Will O2 oxidize chloride? No, because if O2 oxidizes chloride, we'd form chlorine. Well, chlorine is stronger, so we're going from weaker to stronger, and that wouldn't work. Also, it'd form water. And in this case, we're going from weaker chloride to stronger water. And so that wouldn't work either. And so what we can say is that chloride will be oxidized by all oxidizers stronger than what?
stronger
Than chlorine. I'm not gonna, we could talk about reduce, it'll reduce any, I guess I should say that too. Chloride will reduce any oxidizer stronger than chlorine. So that's the chart method. We use the chart. The chart is good. Not only is the chart good at this, but let me talk about another advantage, because if we try to analyze the redox properties of HCl just using what we know, single replacement, combination, decomposition, those kind of things, it would be very difficult. And let me talk about another advantage. So the chart method was good for analyzing the redox properties of HCl, but it also avoids this problem. The second problem that we see in following certain patterns, always great, right? As long as they work. But a lot of these patterns don't work so well sometimes. So an example of where a pattern kind of fails is something like this. If I try to do this reaction using the single replacement pattern, what do I end up with?
HCO or CN. Copper.
A plus BX.
It's copper nitrate.
Okay, now do I form copper 1 nitrate or copper 2?
Copper 2.
It will actually be copper too.
Yeah, that's tricky. But it turns out it's copper 2 is a more favorable charge on copper. We can see that here. When we see copper metal only occurs once on this chart, and it forms copper 2. There is a possibility of forming copper 1, but it's under other conditions. And so if we form copper 2, it would be copper with 2 nitrates. Nitrate's a -1. So we'd form copper 2 nitrate and hydrogen gas. So we'd look at this. We'll need 2 to balance that. And then we're going to use the activity series. We have an upside down activity series. And so we're going to compare hydrogen with copper. So this is an upside down activity series. This is saying hydrogen is more active than copper. Right? Lithium's down here. So that means we're going from less active to more active. And the activity series says, no, that's the wrong direction. The driving force is this way. And the driving force is this way, therefore we get NR. NR stands for no reaction. But it turns out this is wrong. And you go, wow, it's wrong. Is it because water? No, water is not going to react with copper. What's going on? And it's not going to react with HNO3. HNO3 was already a strong electrolyte. So it's not the solvents, What's wrong now? I'll tell you the next thing that's wrong with this is this. When you fix yourself to this pattern, this is an analogy I use, is you assign roles. And when we assign the roles, let me see, they can be misassigned. So the A plus B X pattern, you're locked in to the roles. And the roles are like this. A, you're the director, and you're the director of the play or whatever. And you say, okay, A, what's your role? And so what's A's role? Well, A is going to be the
Lead.
reducer. And then you go, B, okay, B, your role is to be the oxidizer. And X, your role is to be the bench warmer or the standby or the spectator. And so X is going to be the spectator. It's not going to play any role. If we go back to the chloride, did the chloride play any role? The chloride just stayed chloride, didn't it?
Yes.
Right. And so when we look at the roles here, copper, okay, that's okay. That was pretty well selected. Copper is a pretty decent reducer. And then you assign, okay, H plus, you're the oxidizer. And the nitrate, you just watch. But when we look at this, does that make sense? Because where's nitrate? Here, where's H plus?
Down there.
Down here.
Which one's a stronger oxidizer?
I know.
Nitrate. Do you think nature is going to care about how you assign the roles?
No.
No, I think like nature is going to just,
Be unpredictable.
well, it's unpredictable if we do this. It's unpredictable, but we should be able to predict that nitrate's not going to be happy as a spectator. Do you think nitrate's going to be happy as a spectator?
No.
No, this is completely misassigned. Nitrate is not going to be happy as a spectator, and nature doesn't care what you want to do. And so you could tell nitrate you can't react. But do you think nitrate will listen?
No.
No. And so when you assign it an A plus BX pattern, you're telling nitrate you can't react, but nitrate's not going to listen, and what's going to happen? Nitrate's going to react. And so in order to do this, this one requires a chart method. And so you have a choice here. One, you can memorize. We have two types of acids. We have mineral acids and we have oxidizing acids. Mineral acids, the anine's kind of a spectator. Oxidizing acids, the anion is not a spectator. And so a mineral acid would be like HCl. That's a mineral acid because chloride, so you can spectate. But if I had sulfuric acid, H2SO4, look at sulfate is more powerful than H+. So therefore we call sulfuric acid an oxidizing acid, not a mineral acid. What else? Nitric acid. Nitric acid consists of nitrate and H+.
What about iodine?
Iodic acid, oxidizing acid. Perchloric acid, oxidizing acid. So one thing is, if you like single replacement, you're going to have to treat oxidizing acids differently than mineral acids. If you do single replacement, you got to know that you have potential for failure for oxidizing acids. The next would be something like this. Let's go. Let's take a look at the roles. A is what? A is the oxidizer. B is the reducer. X is the
Spectator.
Spectator.
What is that?
do you think chlorine's going to make a great oxidizer?
No.
I think no.
No, not going to.
Actually, chlorine is a good oxidizer, great oxidizer. But you know what? This isn't the role I was supposed to assign. The role I was supposed to assign is A is not an oxidizer. A is the reducer. Do you think chlorine's going to make a good reducer?
No.
No. Do you think chlorine wants to give up electrons? Not at all. Chlorine wants to take electrons. And so when we're locked in, because we're locked in, we can't change that because A plus BX pattern requires A to be the reducer. And it requires B to be the oxidizer. So chlorine versus potassium ions. Chlorine is here. Potassium ions are the second worst oxidizer on the chart. Who do you think is going to be the oxidizer? Chlorine. And therefore, single replacement fails. But what you could do is you could memorize a second single replacement pattern. The second single replacement pattern is the X2 plus AY yields AX plus Y2 pattern. Do you want to memorize that one? This is the single replacement pattern for halogens. Yes? if you want to stick with single replacement, you have to know this one too. Or, if you don't want to memorize this, then you just use the
Sure.
chart method. So, you have two choices here. One, memorize oxidizing acid versus mineral acids. Know that the single replacement fails for oxidizing acids. Two, memorize the halogen single replacement pattern. And then you can continue using single replacement without having to worry. In Chem 4, you never had to worry because, you know why? They didn't give you these. You know, they didn't want to mess things up. They wanted the single replacement pattern to work perfectly each time. Right? So the way to make it work perfectly each time is to eliminate all the ones that fail. In Chem 1A, they aren't going to be as nice. They're going to throw in some failures in there. And so you have a choice. The choice I do is I just say, if I already know, I already know these patterns, so I'll just do either way, whichever. Leave it up to you. Okay, so those are some common failures. So let's do what next? The problem with the chart method, is there any problem with the chart method?
Takes a long time.
The time it takes.
Yeah, and there's other problems with the chart method that I didn't tell you. Let me tell you some other problems with the chart method. Is that chart comprehensive? No. So you know where you can find a more comprehensive chart?
Activity. It's just,
Where do you, in your book.
oh,
But where in the book do you think you can find a more comprehensive chart?
chapter 24 section.
No.
Dang it.
Not in the index, close to the index.
What is your professor? What was the passion of the professor? Are you not at liberty to
Appendix
say-
D.
Appendix D.
Appendix D. You can find a more comprehensive chart in Appendix D. But is that completely? No, it's not comprehensive. So there's some stuff out of there. The other things are, you know, this is under standard thermodynamic conditions. What are standard thermodynamic conditions? Standard. Oh, go ahead.
Oh, STP, right?
No, not STP. That's standard temperature and pressure for gases.
Oh. Then would it be room temperature?
There's no standard temperature, but most stuff is given at room temperature. So one, this is for room temperature. Two, this is for standard conditions. This little superscript 0 means standard conditions. Standard conditions means that the gases are at 1 bar or 1 atmosphere and that the solutions are at 1 molar concentrations. So if you change the pressure or the concentration significantly, it changes the reactivity of these things. And so that's going to change things to an extent where what you predict might not actually work out. So that's one of the disadvantages. What if you're under non-standard conditions? If you're under non-standard conditions, then we have to do what are called thermodynamic calculations. Those are talked about in Chem 1B. So we're going to restrict ourselves to standard conditions at room temperature. But still, it's not. What if something doesn't occur on the chart? There are lots of those types of things. Then we have something called skeleton. So let me talk about skeleton. me just do something. With skeleton redox, you know, you just mix it and see what happens. So an example would be, I'm going to mix methane and oxygen and see what happens. If I mix methane and oxygen and see what happens, and I generate a whole bunch of carbon monoxide gas, right, then I'd want to balance this. Uh-huh. What's that? When are we going to finish the lab? We're going to work on the lab. Do you know the lab is a demo lab? And so I'm going to go through it, but
Even the second part of it?
the second part of which lab? Actually, we haven't even finished the first part. And so we're going to, are you worried about not getting the data?
I just don't know when are we gonna do it? Are we gonna do it like the next lab day?
No, we're going to stick with the lab schedule as written, but what I'm going to do is I'm going to just fit in whatever I can fit in to the labs. These labs, this series of labs, 17, and what was the redox one? 18? 18. These are all chemical reactions labs, and so we're going to go through those. This one is demo, and so I'll just do those, but the 18 you're going to do some hands-on, so you don't have to worry about collecting any of the data for this particular lab, because I'll give you all the data that you need. So don't worry about running out of time. It's not like I'm going to say, okay, go ahead and start, and you'll have 10 minutes to finish the lab. That's not going to happen. So if you're worried about that, don't worry about that. The other thing is this. Don't, you know, if you did this lab before, let's say in the past, you know, every semester I do it a little bit differently because I don't want people to copy like other people's lab data or lab reports and turn those in. So everything's going to be a little bit different each semester. I do this just to prevent that, because in the past I've seen that quite a lot. And so I eliminate certain parts, and you might notice that. So if you're working with friends and the friends are taking another professor, it might not be exactly the same, you know, what we're doing versus what they're doing. And so just be aware of that. And I look for that also. But anyway, this is an example of skeleton redox. In skeleton redox, this is the way we normally handle it. Now, for something like this is easy to balance because you know what the products are. But let's say we didn't know what the products are. And so the first thing we do in skeleton redox is we separate this into half reactions. So methane ends up in CO. And oxygen ends up, well, we don't know where it ends up, but it doesn't matter because oxygen and hydrogen end up somewhere, and we don't have to worry about that necessarily. And so in skeleton redox, which element do we balance first? All elements other than hydrogen and oxygen. Does this sound familiar? And so over here we have one carbon, and this is the way I write it, and one carbon. So the carbons are balanced. Okay, after we balance all elements other than hydrogen and oxygen, then we start with the oxygen. And so over here on the left I have 0 oxygens. On the right I have 1 oxygen. And so how do I balance oxygens?
You add air.
Do I add an O?
Air.
Oh, you can add O2.
Do I add an O2? No, I add a H2O.
No, yeah.
It's kind of weird, but do you guys remember this? Is this coming back? Then after I balance the oxygen, actually I have 2 oxygens. No, 1 oxygen. Then I balance the hydrogens. How do I balance the hydrogens?
By adding water.
Getting close. So we have a total of 4 plus 2 gives me 6 hydrogens on the left. And then how many hydrogens on the right? 0. And then I have what? Balance the charge. Not adding protons, but adding electrons. So when we balance, oh, actually here, sorry, balance the hydrogens. I jumped ahead 1 step. So we balance the hydrogens by adding protons, you're right. And so if I have 0 hydrogens here, I need how many protons here? 6. Now I balance the charge. And so the charge on the left, 0 and 0, it gives me 0, and then 0 for carbon monoxide and plus 6 means I need how many electrons? 6 electrons. And so what I end up with is the balanced half reaction. So I'm going to have CH4 plus H2O yields CO plus 6H plus 6 electrons here. Okay, then I repeat that for this side. So there are no elements other than oxygen or hydrogen. So I have 2 oxygens on the left. How many oxygens on the right? 0. And so that's going to give me 2 waters on the right. And so this question mark is actually 2 waters. And then I balance the hydrogens. 0 hydrogens on the left, 4 hydrogens on the right. And so I'm going to balance this by
Adding 4.
4H plus. And then I look at the charge. 0 plus 4, it gives me plus 4 on the left. And then 2 waters is 0. And then that means how many electrons?
Plus 4 electrons.
Plus 4 electrons on that. And so the other half reaction is this. It's going to be oxygen plus 4H plus 4 electrons yields 2 waters. Okay, then what do? I combine these two. When I combine these two, I have to make sure that the electrons lost is equal to the electrons gained. So the first one is I'm just going to cross multiply. So the first one I'm going to multiply by 4. The second one I'm going to multiply by 6. Actually, no, I probably shouldn't do 4. I probably should just do 2. Let's go with 12. Would be the simplest factor here. So if I do 2, that gives me 12, and I'll multiply the second one by 3. And so that should work out. Okay. And so this is going to give me 2 methanes plus 2 waters. So I'm going to take all the reactants here and combine them with all the reactants here. And so this is going to be plus 3O2 plus 12H plus 12 electrons. And then I'm going to take all of these products and combine them with this product here. And so this is going to give me 2 COs plus 12H plus 12 electrons plus 3 times 2 is 6 H2O. Okay, then I'm going to simplify. So the 12 electrons cancel, and then the 12 H pluses cancel. And what do I have with H2Os? I have 2 H2Os here. I'm going to cancel out 2 of the 6, so that's going to give me 4 left over. And so what I'm going to end up with is 2CH4 plus 3O2 yields 2CO plus 4H2O. And you go, that was too much work. I could have balanced this a lot faster, right? If you knew the other product here, which would be water. And so this is the skeleton. The major reactants and the major products are given. We didn't have to predict them. They're given. If you look at this one, does this one look familiar? O2 plus 4H plus 4 electrons yields 2 water. And that one is actually familiar. O2 plus 4H plus 4 electrons yields 2 water. And so we could have gotten this one from the chart here. This one we wouldn't have gotten from the chart. And so this is the skeleton method. The major products are given, so we don't have to predict what they are. All right, so experiment 18 deals with redox. You're going to have to do this for the redox reaction in that experiment. So let's take a look at, since I'm talking about it right now, that will save me time next time, but let's do an example here. You know, some of you have heard this story, but I went camping in Joshua Tree, and I stopped by the dollar store in Yucca Valley, pick up some supplies there. And when I was in there, they had a $1 bottle of Santa Barbara wine. So I thought, oh, that's great, you know, $1 bottle of wine for the campfire. And so I took it back, and then I took a sip of it, and do you know what it tasted like?
What?
It tasted like vinegar. This is what it tasted like. And so what had happened? Well, what happened is there's ethanol in the wine, and a little bit of oxygen must have leaked in there. And when that little bit of oxygen leaked in there, it oxidized my ethanol to acetic acid. So this is an example of a skeleton redox. Wines, you know, wines have sulfites, and the job of the sulfite in wine is to act as an antioxidant. But what must have happened is so much oxygen must have leaked in, it must have consumed all the sulfites in the wine, and then it started to attack the next, you know, the sulfites would be the strongest reducer. And once the strongest reducer has been consumed, we're only left with ethanol. Ethanol would be the next strongest reducer because this is fairly electron rich. It's a good reducing agent. But I didn't completely oxidize it, because if I completely oxidized it, it would have gone to, well, if we completely oxidize ethanol, it goes to, not, this is acetate here, or acetic acid. But if you well, let me phrase it differently. If you burn ethanol completely, it burns to CO2. And that would have been great, because then I would have had sparkling wine, non-alcoholic, but that's fine. I would have enjoyed that. And so if there was enough oxygen to convert my ethanol to CO2, then it would have been bubbling wine. But there wasn't. Instead, I got vinegar. And so what happened here? And so we do the same thing. You know, this is an example of skeleton redox. I didn't predict it. This is just what happened. And so we take our ethanol, CH3CH2OH, and then that gets converted into
CH3COOH.
yeah, aka acetic acid. And then the O2 gets converted to question mark. O2 we don't have to worry because it's oxygen and hydrogen. Oxygen and hydrogen are always balanced in the end, because if the oxygens aren't balanced, we add
Hydrogen. I mean water.
water.
Sorry.
No, that's fine. And then if the hydrogen's not balanced, we add H+. And so going back to this, we balance all elements other than hydrogen and oxygen. So this has how many carbons? 2 carbons. This has
2 carbons.
So it's already balanced. If they aren't balanced, we have to change it by using the coefficients. We can't add carbon to this because there's no soot here. Okay, then we balance the oxygens. Over on the left I have 1 oxygen. Over on the right I have 2 oxygens. And so how do I balance?
Add water.
Add water.
And water.
And then how many hydrogens do I have on the left? So that's 3 plus 2 is 5, plus 1 is 6, plus 2 is 8. How many hydrogens do I have on the right? 3 plus 1,
Is 4.
4. And so how many H pluses do I have?
4.
4 H pluses. And then I balance the charge. When I balance the charge on the left is,
0.
the charge on the right is
Plus 4.
plus 4. And so that gives me, how many electrons do I need to add?
-4.
Well, I need to add 4 electrons. That would give me -4.
+4.
So plus 4 electrons. And so the balanced half reaction here is CH3, CH2OH plus H2O liquid is going to give me CH3COOH plus 4H plus 4 electrons. Is this half reaction on the chart? No, it's not. We don't see acetic acid as an oxidizer, but acetic acid can be an oxidizer here. And the reducer here is ethanol. But that's the half reaction here. This one is on the chart because O2, when they're not balanced, is going to form water. And so I could just copy this one off the chart. And in fact, that's what I'm going to do. I'm just going to copy it. O2 plus 4H plus 4 electrons. This is going to be O2 plus 4H plus 4 electrons yields 2 water. That's it. And then what do? I'm going to add these together. But in this case, they add up quite nicely. Because over here, I have 4 electrons lost. Over here, I have 4 electrons gained. And so I'm just going to add them straight. That's going to be ethanol, CH3CH2OH, plus H2O. Okay, those are the reactants on this equation, plus the reactants on this equation here. Plus O2, plus 4H plus 4 electrons, yields acetic acid, CH3COOH, plus 4H plus 4 electrons, plus 2 H2O liquids. Okay, then we simplify. 4H pluses cancel, the 4 electrons cancel. And so the overall reaction here is CH3, CH2OH, plus H2O, plus O2 yields CH3COOH, plus 2H2O. This reaction happened. Since this reaction happened, reducing agents give up electrons, oxidizing agents take electrons. And so oxidizing agents take, reducing agents give up, going backwards. So we're using the conjugate pairs here. And so the reducing agent would be ethanol and water. This is our RA. The oxidizing agent would be here, O2 and H+. The H+ got canceled, so we'll just do O2. And then acetic acid here will be our conjugate oxidizer, and water here will be our conjugate reducer. And so this reaction happened, meaning that ethanol in water is a stronger reducer than water, and acetic acid is a weaker oxidizer than O2. So we're going from stronger to weaker. So this is driving force. And that's because this happened. We know it happened, therefore there's driving force for this. And so this is what happened to the wine. The wine, we call this partial oxidation. Just like I had partial combustion of methane, that partial combustion led to carbon monoxide. This is partial oxidation. Full oxidation, if I drank the wine and I consumed the ethanol, do you know where the ethanol would have ended up? The ethanol would have ended up in my breath because I would have exhaled what? CO2. So if I had the chance to metabolize this ethanol, it would have been metabolized completely to CO2. And then it would have been completely devoid of energy. You know, ethanol contains energy. We can use that as fuel. CO2 is what we exhale because our bodies are very efficient. They want to maximize the fuel, right? If you drank wine and you started exhaling vinegar, acetic acid, then you aren't maximizing digestion or metabolism of the ethanol, right? That's partial. And so when we have this, I mean, under what conditions do you have this? Well, the oxygen must not have been intense enough to oxidize it fully. Was there a question, Elizabeth?
Yeah. Do we need to cancel the water on the left side so we can have water on the right side?
Oh, yeah. Right. Okay. And so now it's just ethanol and oxygen. That means my reducing agent is going to be just the ethanol. My oxidizer will be the O2. That's good. How can I check? When we check these, we check for atom balance and we check for charge balance. And so I want to just double check to make sure I didn't make any other mistakes. So I have 2 carbons, 2 carbons, 5, 6 hydrogens, I have 3, 4, 5, 6 hydrogens, 1, 2, 3 oxygens, 1, 2, 3 oxygens. So the atoms are balanced. Then I check the charge, 0, 0, 0, 0. So the charges are balanced, and then it's right. And so this is correct now. So this is what we call a hybrid skeleton. Hybrid because this one I had to do skeleton, this one I just got off the chart. So a lot of these you can get off the chart, but not all of them, because not all of them occur on the chart. The chart is not comprehensive enough for everything to occur there. So I talked about all the reaction types. And so what we're going to do is we're going to do some prediction for this. And that's why we want to learn this. We want to learn this stuff so we don't have to actually do it. We can just predict what's going to happen. Because I'd rather not have to do these. I'd rather you just tell me what's going to happen and your prediction should come out correct. Okay, so now I know what, but like again, I do these a little different than the report. This is why I say write your observations in your notebook, not on the report sheet. Actually, I might know where to go. And we're just going to do it based on what I do, not what the report sheet says to do. And so there's certain reasons I do certain things like that. One, because I run short on time, and two, because I don't want you copying other things or doing that. Because a lot of people think, okay, get it out. Okay, so as far as electrolyte properties go, did we use distilled water?
Yes.
No, because I didn't have any distilled water. I was looking for it. They didn't give me any distilled water. So we used, so that was one of the first things that you should correct in that. You know, the report sheet says to use distilled water. We certainly didn't use distilled water. It's too pricey, too expensive for us. And so I would expect to see deionized water, you know, not distilled water. And if you wrote distilled water, then I would think, you know, maybe you weren't here or weren't paying attention to what was going on. Okay, the next would be, after that we did tap water.
Yes.
Right? And tap water, what did you write down? Was it a...
Conductive?
Yeah, weak conductor of electricity, but it did conduct. And it asks you, does it ask you for major species and minor species?
Yes, it does.
The major species would be, what? That one's a little bit trickier because you could just say there are electrolytes, dissolved salts, like sodium ions, chloride ions. Those are the major conductors. The major species is H2O molecules, but H2O molecules themselves don't conduct electricity, right?
So the major one would be salts.
Yeah, dissolved salts. We'd like to know what those are, but you know, it varies a little bit. It's like, you know, the like if you go up to Mammoth or Yosemite or someplace like that, and you drink the tap water. You know, when you drink the tap water there, it's like mountain spring water. It tastes pretty decent compared to around here. Okay, what's next?
NaCl solid.
Okay, solid sodium chloride Is it going to conduct electricity?
No.
Well, it has plenty of ions, so will it conduct? Let's check. So let me just make sure this is working. So I'm going to get my solid sodium chloride. I don't have a beaker for that. Will it conduct?
No.
Why?
Because they like to stay together.
Yeah. Yeah, not portability. Another word for the same thing.
Mobility.
Kind of mobility. Right. It's lacking mobility. How can I? Right now the ions are locked in the lattice. How can I free them up? I could dissolve it in water, or I could melt it. The problem with melting sodium chloride is its melting point is over 800 degrees Celsius. It's too high. And so rather than melting it, I'm going to dissolve it in water. When I dissolve it in water, it's going to do what? Free up the electrons. I don't even need this much. Normally we don't pour chemicals back in here, but this one's just used for this, so it's all right. So I'm going to do this. I'm going to dissolve it in water, and let's see what happens. So it becomes a strong conductor.
So it is a strong conductor or a non-conductor?
Strong conductor.
Or NaCl solid?
No, NaCl solid is not.
It's NaCl.
Yeah, NaCl solid doesn't, because the ions are locked in the lattice like this. This since this is a demo lab, attendance is important for this one.
Difference between pulling apart graphite and difference in pulling apart latex or rubber. You can pull apart latex and rubber.
Yeah.
You can't pull apart graphite. You can break graphite, but you can't pull it apart.
Graphite's a weird one because you can pull apart sheets of graphite when you have single crystals.
Yeah.
And so it's actually kind of weird, but anyway, this one, the ions are locked in the lattice, no mobility. What was the symbol we gave to mobility?
Mu.
Mu. So I'll just write no mu. That's it. But when we dissolve it in water, we'll form NaCl aqueous. So the first thing is group 1 salts are soluble. And soluble salts are strong electrolytes. Soluble salts are strong electrolytes. What does that mean? That means
That they break apart easily.
into what?
Ions.
Okay, what are the ions they break apart into?
Na plus and Cl minus.
In Cl minus. And so these aqueous ions are free. And so if I plug in one, what we call electrode, one piece of metal, and it's positive, and another electrode negative, we'll have conduction. And that is the sodium ions will travel to this electrode, and the chloride ions will travel to that electrode. So we get electrical conduction. So we got mobility. All right, what's next?
I may have missed it, but what do we write under electrolyte type?
Next is
Electrolyte type. Now, the electrolyte type, like for example, tap water. Tap water was a weak conductor of electricity or a strong conductor of electricity?
weak conductor.
Weak conductor. Is tap water a weak conductor because it has weak electrolytes in there? Like heavy metal salts and weak acids and weak bases? Is that the reason why? No. Tap water was a weak conductor of electricity because it had strong electrolytes, but the concentration was very low. And so conductivity is going to depend on N, mu, Z, or E. What did I write? E? E. M, mu, E, or Z. E and Z are used interchangeably for charge. The number is very low. And so it depends. If you're a battery person, you would say weak electrolyte. This is weakly conducts. But the definition we're going to use is it's a strong electrolyte, but the concentration's too low. And so that's why it was a weak conductor, but there's strong electrolytes in there because soluble salts are strong electrolytes. And so the electrolyte type, strong but low concentration.
Oh, should we write low concentration?
Yeah, strong but low concentration. For electrolyte type. Now, if I put seawater in there, what do you think? Strong.
It is strong.
High concentration. It would light up brightly. You know,
Because
ocean.
it's salty.
It's really salty, but when you drink tap water, does it taste salty? Can you even taste the salt? I can't even taste the salt in tap water. But it's there, otherwise it wouldn't conduct electricity. Okay, what's next?
Potassium chloride.
Potassium chloride.
Solvent.
That's a solid. Yes, that's a solid first.
Okay. So I'm going to take some solid potassium chlorate. I had cleaned these electrodes before, but they're dirty now. So I have my solid potassium chlorate. Will it conduct?
No.
No. Why?
Because the bonds.
No mobility, yeah. Again, no mobility. The potassium chlorate is a heck of a lot easier to melt than sodium chloride. And so I'm going to melt this stuff.
Not to start using Bunsen burner.
I'm sorry?
Not to stop using the Bunsen
Yeah,
burner.
that's what I'm going to do. I've tried to melt sodium chloride before. It didn't. It didn't go. I didn't do anything. It didn't get hot enough. But potassium chlorate has a fairly low melting point, so I can melt this stuff without too much difficulty.
Professor, you just need to get your arc furnace. Keep at home. Bring it up over 1,000 degrees.
Actually,
Not solid English.
yeah, that would probably be pretty good. Well, I used to work with a platinum oven. Platinum oven, the heating element was made out of solid platinum. It was expensive at that time, but it'd be ridiculously expensive now.
Because it's made of pure black.
Yeah, I just wish, I wish that thing went bad and they surplused it and then I bought it. There'd be pounds of platinum in there. Sometimes you got to watch out because sometimes the schools, they surplus stuff that's very valuable. We had a lot of silver nitrate, and they said, it's getting too messy. There's too much silver nitrate here, so they surplused it. And when they surplus it, they sell it to auction. And the person who bid on it barely paid anything for it. And then silver prices skyrocketed. And now we have to buy silver nitrate, but we can't afford it. It's one of those things. I didn't want to surplus it because silver is expensive. But I was outvoted. Anyway. I should have bought it, though. I was thinking, man, let's surplus that. Let's surplus all our platinum. Then I'm going to be on the auction site bidding it up. You gotta know that. You gotta know that happens. That's gotta happen. I mean, think about that.
I'm gonna wait for the day they surplus the gold.
I'm thinking, I gotta keep an eye on the military surplus and stuff like that and see, Maybe it's getting harder because people are aware of that, but look out for these auctions. You can pick up some probably good deals. The person who bought that silver nitrate got a great deal. I could have bought it and then just recovered all the silver. Oh well. Didn't think about it at the time, but now thinking about it because the prices of everything are crazy. All right, so what I'm doing is this is common. These burners are meant to be held in your hand, so in case things go too hot, you know, and it starts to splatter, I don't want it to hit anybody. So if it starts happening like that, then I'm going to pull this away. But since you guys don't have goggles, I'm the only one who's protected
What
here.
are you talking about, Professor? I'm protected.
Oh, okay. Then I should move the apparatus right in front of you guys. Okay. All right, thanks. That makes me feel more comfortable. So I want to try to get a cone, and then I want to hit the tip of the cone. It's kind of dark here. It's hard to see, but the thing I worry about is it's just not melting. You know, it's not like melting sodium chloride or potassium chloride. It's chlorate. What am I worried about? Chlorate. Chlorate.
Gas.
Well, I'm worried about gases forming, for sure, but one of the chemical properties, tell me a chemical property of chlorate.
It's reactive there.
Chlorates, do they precipitate out with anything, metathesis-wise?
No.
No. Chlorates are pretty unreactive, but that's only for metathesis. Are chlorates a very good base? Chlorates are one of the worst bases.
Yeah.
They're so weak, they're considered neutral. Is chlorate a strong reducer? Reducers are electron rich, so would you call chlorate electron rich or would you call it poor?
I would call it.
I would call it poor. Draw out the formula ClO3 minus. Tell me what the oxidation state on chlorine is.
How could be +5?
Plus 5? Is that a happy oxidation state for chlorine?
Oh.
No. This is why it's a little bit dangerous to melt. It's a little bit dangerous to melt potassium chlorate because if there's any oxidizers around, you're going to have a violent reaction. In fact, a lot of people like to do this. A lot of people like to get molten potassium chlorate, and then do you know what they like to do? They like to drop gummy bears in there, and then they have these little explosions with the gummy bears. Have you seen that?
Oh yeah, because the gummy bears have air pockets.
Yeah. So what I used to do is I used to drop paper towel in there and watch it ignite. But this is now it's molten. It just wasn't deep enough. So I have molten potassium chlorate there, and molten it breaks apart the ionic bond, so now you have mobility. The ions are free to translate and move around, and so molten potassium chlorate conducts electricity. I would do the paper towel thing, but our smoke detectors are too sensitive here, and so it might trigger a fire alarm. But if I drop paper towel in there into molten potassium chlorate, you're going to get nice little fires. Yeah, this is a strong conductor. Electricity.
Is it still a strong electrolyte if it's in its solid form?
To a battery person, yes. This is a strong electrolyte. To our original definition means dissolved in water, and this is not dissolved in water. And so the whole thing about those definitions is, it depends on who you're talking to. And so you could say it's a strong conductor, strong electrolyte. You could say that. Yeah. But normally what we say is, does it break up into ions? Because solid sodium chloride, was it a strong electrolyte? Well, it depends. If you're saying, okay, I need some more electrolytes because I'm going on a jog, then yes, because you're going to dissolve in water, it's going to be electrolyte. But if you're a battery person and you're looking at, does solid sodium chloride conduct electricity? No. Does solid potassium chlorate conduct electricity? No. So, but you'd still call it electrolyte. It's a good electrolyte because it's a salt, soluble salt. Don't use potassium chlorate though, if you need electrolytes for your job. This chlorate is pretty reactive. Potassium chloride, yes, no problem with potassium chloride, but chloride versus chlorate, huge difference.
Professor?
Uh-huh.
In the front of the book, the front of the experiment, it says solid salts with food structures do not conduct electricity, therefore they are not electrolytes.
It depends on what definition you want. That's correct if you use the definition for a battery person. But it's not correct if you use the definition for electrolytes in general. So, you know, because of this, I don't really want, because of this, I don't really want to get into the arguments for,
Say high mobility, low mobility for
yeah, it's just better just to think what happens, in terms of number, mobility, and charge. And then, no, if you have a lot of mobile ions, then it's going to be a good conductor. And if it's a good conductor, then you can call it. Yeah, that's... Some people are very strict about the definition, and that type of stuff, but I don't want to get into that too much. Okay, I'm going to cool this down to solidify it. When I cool it down to solidify it,
Oh, I was going to ask for potassium chlorate as a liquid. Would the major species just be potassium chlorate, or would it be potassium and chlorate as a cation and an ion?
This is what we do for the potassium chlorate. So we take potassium chlorate, solid, and then heat it up. Do you know what the symbol for heat is? Delta. And then what we get is KClO3 liquid.
So it didn't change at all. Just states.
It did, but what we can do is we can write this as molten potassium ions and molten chlorate ions. These are now free. They're not bonded together. They're still stuck together because of the electrical attractions, but they have what we say is translational mobility, the translational motion.
So is the solid in like a structure?
Yeah, the solid is going to be in a crystal lattice. Now chlorides are round, but chlorates are not. Chlorates, what is the structure for chlorates? Chlorates are trigonal pyramidal. So you have these trigonal pyramidal anions. I'm not going to write it all out. But you have this locked in a lattice. And so this would just be a lattice here. Okay. And then when you melt it, you break apart the lattice. So in a lattice, we have an orderly arrangement. But in the molten salt, it's going to have some disorder to it, because they're all moving around. And so it's not going to be an orderly arrangement. And so this is nice crystalline, but the liquid would be kind of amorphous and in motion. I don't like this lab because of the electrolyte. I don't like talking about strong, weak, and non-electrolytes usually, unless because it always leads to confusion. Do you see it starting to cool down?
Yeah.
Yeah.
It's starting to flicker.
I was going to thermal shock this, but I think I can avoid it.
The thermal shock is so much fun. It's how I break my glasses.
Yeah, okay. Let's try thermal shock. Ran out. Maybe this is not enough. Do you see the what's keeping this molten? Do you know what's keeping this molten?
The electrons passing through.
Yeah, the electrical current. Actually, there are no electrons passing through
Oh,
this.
sorry, the electrical current passing
Yeah, the electrical current passing.
through. Could you turn it on?
Yeah, I can unplug it and then plug it back in. That's going to be the only way, it looks like. Okay, let me cool it down a little bit more. Let's plug it back in. Okay. So now it's solidified. Still working. Okay, but now what I'm going to do is rather than melting this, I'm going to dissolve it.
Yeah.
And so when I add water to this, it'll free up the ions. And then conduct. Okay, I'm going to unplug this. Oops. All right, what's next?
Copper sulfate.
Yeah. Yeah, there's two common charges for copper. What are they?
1 and 2.
1 and 2. And what's more common?
2.
Copper 2 is much more common than copper 1. Let me clean these off. Well, this is just for the demo, so I'm just going to use the bottle. But I don't want, these electrodes are so contaminated, I don't want to contaminate this. I'm going to pour it into a beaker. Do you know what color copper 2 ions are? Is that green or is that blue?
So that's like a blue.
Yeah, most people call it blue, but I don't know.
Same way it oxidizes, it becomes, what is it, green.
Yeah, the hydrate is like green.
Green?
Yeah.
Yeah.
But, yeah, when it's a solid, it turns
Do you know what color sulfate is?
yellow.
Yellow.
I
I think.
Sulfate is colorless, actually.
Or
So the blue color is only due to the copper. Do you think it's going to conduct?
yeah.
Okay, sulfates are all soluble except for which ones?
Silver.
Silver, lead, mercury.
Gold? No.
Silver, lead, mercury.
Calcium, strontium, barium.
Yeah. Silver, lead, mercury, mercury, calcium, strontium, barium. 2 mercuries because mercury 1 and mercury 2 are insoluble as sulfates. Yeah. But copper, everything else is soluble. Plug this back in. So this should be a strong conductor of electricity, right? That's what we predict. We predict in the solution you're going to have copper 2 and sulfate. Strong. Well, it didn't look so strong, but it's strong. All right, what's after copper 2 sulfate? Okay, pure ethanol or aqueous ethanol?
Pure. Pure.
Pure ethanol. Pure ethanol sometimes is called denatured. This is pure ethanol, 100%. 100% is, do you know what proof that is? 200 proof. This is 200 proof. When you smell chemicals, you don't put your nose under it like this. You waft the vapors. So this smells like, this is 200 proof. If you try to drink this, you know what happens? It evaporates so fast. You know, it hits your tongue, it just evaporates. But you don't want to drink this because, I think I told you this. we don't have to pay liquor tax for this. We don't have to pay liquor tax because people won't drink it. They won't drink it because they contaminate this. This is not pure ethanol. This is adulterated ethanol. They put some carcinogen, mutagen in here so people don't drink it. And therefore you don't have to pay consumption tax for this. So don't drink this when I'm not looking. What's it going to do? Is it going to conduct?
No. Most likely not.
Oh, shoot.
What?
You can
I contaminated. I shouldn't. This is called poor technique. Poor technique is do not contaminate your original source bottle. We want to transfer transfer a small portion to a beaker. That way we don't have to contaminate our original.
get a big beaker so you can pour that other beaker.
So when somebody looks at this, there's going to be a chunk of stuff in here. Are we out?
Yeah.
Yeah.
Oh, yeah.
That's fine. All right, so that's it. Then we'll continue this Wednesday. So hopefully nobody notices I contaminated this.
You're not gonna put the label on it? Don't worry, Professor. We won't say.
All right, thank you. It's secret.
So I think we'll be fine with this. We'll be fine.
Okay.
We don't know what type of. I said both of them would be the exact same. It's just anything.